So those are the postulates of quantum mechanics. And now we're going to look at some of the additional properties of wave functions, operators, things like that, that come from some of the properties of that we've defined in the postulates. So one of these is a principle called orthogonality. And this is a consequence of the fact that our operators are linear, as well as the fact that we require that the eigenvalues that we obtain from the operators are real numbers. Right, they're not complex numbers because these are things that we can actually observe, and we can't observe complex numbers. We observe, when we look at position and momentum and energy, right, those have specific values that are real numbers. So a consequence of this is that eigenfunctions of these operators are what we call orthogonal. Now we need to define what this means. When we're talking about, you may be familiar with orthogonal, meaning something that's at a right angle, right? So an x and y axis are orthogonal to each other. This is a really related mathematical idea, but when we're talking about quantum mechanics and wave functions, this is defined a little bit differently. So if we have a set of eigenfunctions, so say we have our operator A, and we have a set of eigenfunctions n, and we get multiple eigenvalues from this. So this could be like our particle in a box, right? We have a set of solutions that are the wave functions. So if these wave functions are normalized, which they are supposed to be according to the postulates of quantum mechanics, this whole set forms an orthonormal set. And so let's first define orthogonal. What that means is if we take two of these wave functions, so if we have psi n and psi m, right? So say for the particle in a box, we have psi when n equals 1 and psi when n equals 2, psi 1 and psi 2. It just as a specific example. If we take the integral over all space, whatever that space happens to be, of psi n star psi m, right? So we're looking at two different wave functions. We get that they're equal to that this integral will equal 0 as long as m doesn't equal n. And if they're normalized, if m equals n, then the integral is 1. Whoa. That wasn't supposed to happen. Let's zoom back in here. All right. If m is equal to n, the integral equals 1 instead of 0. And so this property of wave functions, we call them being orthonormal, meaning they're orthogonal. So if they're different values, different wave functions n and m, we get 0. And if they are the same, then we get 1, meaning they're normalized. All right, and so we can represent this by this notation here. So integral over all space, psi m star psi n. It doesn't really matter the order here. D tau, I put dx there, right? This is for whatever variables are relevant. We can say this is equal to delta nm. And this is what's known as the Kronecker delta. This symbol here. And what it means is delta nm is equal to 0 if n and m are not the same, and it's equal to 1 if they are the same. So it's just a shorthand way of writing what we were saying about orthonormal. And so in the next video, we'll look at, with a couple of particle in a box wave functions, an example of this being true for that particular system.